Okay, good morning, everyone. Welcome back. So before we dive back into lecture, just a bit of a reminder about how the course is run and all the logistics we went over yesterday. We went over on Tuesday. Just a reminder, when you come to class, be sure to click on the attendance sheet and mark yourself as here. On Tuesday, I uploaded the video for those of you that missed the lecture or wanted to watch the lecture again. I posted the quiz, which hopefully most of you took before midnight on Tuesday night. And the quizzes will always draw on materials from the reading and directly from the lecture notes. If we have any side discussions in lecture, those will not show up on the quiz. Last but not least, I assigned the first of the 10 programming assignments that you'll be carrying out. And as I mentioned last time, for some of you, it might take you less than an hour to finish assignment 1. For others, it might take much longer for various reasons, but the most important one probably having to do with installation. So it's... Shauna says she is trying to open the lecture slides for today and she's getting an access denied error. Okay, just give me one moment here. I might have forgotten to set the write access for those, or the read access for those.
Thank you. Sorry, I'm just trying to follow along and it wouldn't let me open it.
No problem. Yep. Fair enough. Okay.
Also, we don't have access to the reading, which is less important, but...
Okay. You should have access to... You should have access to the slide deck for lecture 2. Can someone just give me a thumbs up or a yes in chat to let me know that that's okay?
I got it now. Thank you.
Great. And I'll fix the read edit for read privileges for the reading when we finish lecture today. Okay. Thank you for that. Okay, so let's talk about assignment 1. My understanding is that some of you Windows users have been having some issues. The first one is that you need to install Visual C++. The reason for that is that the physics engine that we're going to be using in this class, PyBullet, as the name implies, it's a Python wrapper around the bullet physics engine, which is written in C++. So when you pip install PyBullet, your PyBullet is in turn installing Bullet, which requires C++, which is why the Windows users need to install Visual C++. One of you was telling me this morning that you might also need a wheel for this to work. So give that a go. Any other installation issues other than are mentioned here in steps 2A, B, C, and D now? Can people just give me a sense of how we're doing with installation? So for those of you who've tackled installation, can you type yes in chat if you managed to install PyBullet, or no if you're still struggling with PyBullet installation issues? Just like to get a quick sense of where we are with this. Okay, mostly yes. Good. Okay, last year when I ran this course, instead of using the Bullet physics engine, we used Open Dynamics Engine, or ODE, which had many more installation headaches. So hopefully the switch to Bullet and PyBullet will get us all past the installation headaches and onto the fun part of the assignments, which this week is, again, installing PyBullet and then writing a very simple program called Simulate. And Simulate, as the name implies, will simulate an empty virtual world using PyBullet. You'll then create a second Python program called Generate, and Generate will generate objects to populate physical but physics-based, but virtual objects to populate your world. So objects, not to be confused with objects from object-oriented programming. So cubes and spheres and cylinders will be generated eventually by generate.py, which will become your world. Pyrosim is a wrapper that I wrote, which in turn wraps around PyBullet. So this point is a little confusing. There are actually 2 Python wrappers in this class. The lower one, which wraps around the physics engine directly. The one that I wrote specifically for this class hides a lot of the physics details that are not going to be relevant to this class. So physical simulation is a fascinating topic in and of its own right, but some of the nitty-gritty details of physics, like inertia and momentum and tensors and so on, not important for our purposes. So Pyrosim hides a lot of those. It also, as we'll see in a couple weeks' time, it also allows you to create a brain for your robot. At the moment, you're just going to be creating a world. Next week, you'll be creating a body for your robot, and the week after that, we'll be creating a brain for your robot. Okay, so as I mentioned, by the end of 10 weeks, you'll have a good hand. This will be what your code base is, but we're starting very simple this week. George says, for other Windows users, I found it useful to run a PowerShell from the Anaconda Navigator to install it. Okay, so people that have found solutions, George and others, please let me know, and I will just include them in the wiki instructions for everyone to see. Okay, any questions about the assignment, quizzes, video, lectures, how the class is run, anything about logistics? Just a reminder that in Blackboard there's the syllabus that talks quite a bit about how the course is run and the schedule. Caleb asks, when uploading to Blackboard, do we just put the Reddit links in the comments? Yes, the answer is yes. So let's go back to this slide here. So this is an overview. Of how you submit. So remember, you all are starting in Blackboard. Blackboard takes you to Reddit. You go to YouTube to post solutions to the various modules. You create a Reddit post, which includes a link to YouTube. You copy the URLs of the 2 Reddit posts for assignment 1, and you take those 2 Reddit URLs and you drop them in the comments or the submission for assignment 1 on Blackboard. That's how we do the assessment part of this course. As I mentioned, there are online users who are taking this class purely through Reddit, so they get as far as these 2 steps, but obviously not Blackboard. Their work is not being assessed. Make sense? So we actually have 4 pieces in play here: Blackboard, Reddit, YouTube, and along the way, as you're creating your assignments, you are also creating branches from your GitHub repository. The reason why you're creating a branch for each module is so that if you get partway through a module and you get confused and it becomes difficult or impossible to debug your code, you can always roll your code back to the previous branch, which will take you to the start of that module, and you can start working forward again. So for those of you that are not that comfortable with Git and switching and maintaining branches, this week is a good time to watch a YouTube tutorial and learn exactly how to manipulate branches in Git. Any other questions? No? Okay, so just a little bit about the schedule. Obviously, this first week, we're working our way through an introductory module in the course. Last time was all about logistics. Today, we're going to finish up logistics and then move on to a very short history of artificial intelligence and where the field of evolutionary robotics sits in that larger landscape. Next week, we'll spend a little bit of time talking about this concept of embodied cognition, and this is the philosophical aspect of robotics and AI that are often not known by many people that are working in machine learning and artificial intelligence and robotics. But the philosophy underlying these fields influences the kinds of questions that we ask. Okay. Next week and into the following week, we'll have a 3-lecture series on the tools of the trade. So as I mentioned last time, there are 4 basic building blocks that make up an evolutionary robotics experiments. The virtual world itself, and the physical body of the robot inside that physics engine. We're going to have an artificial neural network that's going to serve as the brain of your robot. And then finally, we're going to wrap all of those 3 pieces in an evolutionary algorithm. That evolutionary algorithm is going to tinker with the artificial neural network, and in some cases, the body of the robot as well, to get the robot to do whatever it is we want it to do. Okay. Shauna has a question, has a comment about she's having a problem. Okay, I'll just leave that comment. Again, Shauna, you can post that in Teams if you're asking questions of your fellow students. Of course, by all means, use the CS206 Teams for that. Okay, so that'll be tools of the trade. So we sort of understand what we're building as we go through the assignments. We will then have a longer series on the history of evolutionary robotics. The very first evolutionary robotics experiment was only introduced in 1994, so the field is not that old. But we'll look at some of the first experiments, and because the field is not that old, there are a lot of open questions in evolutionary robotics in particular, but robotics in general. So we'll talk about some of these open questions, like crossing the reality gap. How do we ensure that what we evolve in a physics engine will transfer to physical robots in the real world? How do we scale up evolutionary robotics so that we have thousands of people evolving thousands of robots to perform thousands of useful tasks? We're definitely not there yet. We'll look at some crowdsourcing solutions to that problem. Up until lecture 22, we'll usually be talking about a single robot that is being evolved. In lectures 23, 24, and 25, we're going to talk about evolving swarms of robots, where if there's perhaps there's a task we'd like a machine to do, but that task is beyond the ability of any one robot. How do we evolve coordination and, in some cases, communication among those machines to carry out this task? And then the very last module of the course, we're going to broaden our evolutionary algorithm so that it is not just tinkering with the artificial neural network that drives the robot, the brain of the robot, but like biological evolution, our evolutionary algorithm will simultaneously make small changes to the body plan and neural controller of the robot to try and get it to do what we want. And then again, no exam in this class. You'll be presenting your final projects during the exam period. Okay, so back to course logistics. We were sort of going through the logistics, but we ended. We were talking about the assignment. We ended by talking about the assignment last Tuesday. So I put up here an example of some of the final project ideas that you might tackle. So these are a few that I've thrown out. For example, you might want to ask the question, how do robots with different body plans, so if you have a 4-legged or quadrupedal robot and a 6-legged or hexapedal robot, so you have 2 different robots, you run your evolutionary algorithm on the quadruped for about 8 hours, and at the end, how fast does the evolved quadrupedal robot move? You run you run your evolutionary algorithm for another 8 hours on the hexapedal or 6-legged robot. How far does the hexapedal robot get? If you have enough time, you'll do 8 hours on the quadruped, 8 hours on the hexapod, 8 on the quad, 8 on the hex, night after night after night, and you'll get a growing set of experiments of evolving these robots with different body plans. Which one evolves to travel further? And does that give you an insight into why? So this is sort of a final project about the biomechanics of how 4-legged and 6-legged animals move. You'll see when we talk about evolutionary algorithms, we introduce this concept of a fitness function. So this is a mathematical equation that allows your computer to score how well a robot does. If all you want the robot to do is move quickly, then the fitness function measures the velocity of the simulated robot. The higher velocity, the higher the value of this function, the more likely that robot is to survive and reproduce randomly modified offspring in its turn. That's what we'll be using in the first 10 weeks, but you can modify this fitness function so that it doesn't just select for speed, but selects for speed using a particular gait. So again, back to biomechanics, you can create a fitness function that selects for robots that are exhibiting more of a walking gait and penalizes or does not allow robots to reproduce that do not exhibit a walking gait. Can you create a fitness function for trotting, cantering, galloping, pronking, and so on? If there are any horse people here, there's lots of interesting final projects around the concept of gait. Project idea 3 is, again, to create a fitness function that selects for velocity or fast locomotion, but penalizes for using a lot of energy while it does so. One of the hallmarks of the human species, we tend to focus on our intelligence. We are able to move very long distances using very small amounts of energy. We are one of the most energetically efficient movers on the planet. You might not seem so sometimes. It's very difficult to evolve a robot that moves quickly and efficiently. So that could be an interesting idea. You might put a laser rangefinder on top of your robot and uses that laser rangefinder to look for objects in the environment. You could evolve it to move towards round objects and away from edged objects. You could start to get into some of the building blocks of intelligence. How do you distinguish between friend and foe, food and danger, and so on. I put a couple of links to what I thought were great projects from previous years. One of my favorite is the billiard robot here. All of these project ideas give you a sense of sort of the level of difficulty or the amount of functionality we're looking for in a final project. One of the most difficult questions students struggle with in week 11 is my project too easy or too difficult? So I can't answer, Amanda and I can't answer that question for you directly. Go and have a look at some of the things that have been done in the past to get an idea of what's expected or what's considered a good project at the end of the semester. Okay, so back to our rationale about robotics. Last time we asked why might we want to study or build robots in the first place. There are good engineering reasons, there are good scientific questions, there are good philosophical questions for studying robotics. We're going to focus on evolutionary robotics. So what is the advantage, as we'll see a little bit today and next week, within the field of robotics as a whole, there are different branches of robotics. There's industrial robotics, which we talked about last time. We're going to focus here on evolutionary robotics. What is the advantage of evolving a robot rather than programming it or training using a learning algorithm to train the robot? The first reason why an evolutionary algorithm is useful is that trying to sit down and program a controller for a robot by hand is extremely difficult. If you want to program an industrial robot in a factory that does exactly the same thing over and over again, that's possible. But adapting a robot to adapt or do different things under different circumstances is pretty difficult. So just to give you a sense of how hard this is, here's a particular robot in the bottom left. And this robot is called the nonaped, because if you look carefully, you'll see it has 9 legs. 1, 2, 3, 4, 5, 6, 7, 8, 9. These black bars are carbon fiber tubes. And the body of the robot is made up of 2 Stewart platforms. And I put an animated GIF in the top right here of a single Stewart platform. As you can see, one of these platforms has an upper and lower plate, and it has 6 pistons. You can just see the 6th one in the background there. 6 pistons, and in this case, the pistons are just increasing and decreasing in length at a regular sinusoidal pattern. But each of these 6 pistons is extending and compressing at a different phase offset. So they all have the same velocity. the rate at which they shorten and lengthen, but their actual length at any given time is different from each other. You'll notice that if you pull and push on these pistons in different ways, you can change the relative angles of the upper and lower plates. If you take two of these Stewart platforms and you glue them end to end, you get the nonaped. Here's one Stewart platform and here's a second one. So the nonaped has 9 legs and it has 2 Stewart platforms. Each platform has 6 pistons, so the nonaped has a total of 12 pistons. Let's imagine we wanted to try and program the nonaped to move. And I'm going to show you just a few seconds of this video so you get a sense of what the nonaped's movement can be like. Okay, I'm just going to pause things there for a moment. So you can see that obviously changing, extending and compressing these pistons causes the nonaped's body to extend and compress and twist and so on. And you can imagine that if you get the phase offsets of these pistons just right, or you program when these pistons should increase or decrease in length just right, you should be able to get this nonaped to move forward. Let's imagine we're not going to use a neural network to control the nonaped for the moment. We're going to use something much simpler, which is simply a matrix, a binary matrix of +1s and -1s. Imagine that this matrix has 12 rows that correspond to the 12 pistons that make up the Stewart platform, and each column corresponds to 1 second. So the left-hand column here at T1, at 1 second, we want the motor attached to piston 1 to increase or extend the piston. Motor 2 attached to the second piston is going to compress that piston. Motor 3, extend, and so on. At the next time step, at 2 seconds into the lifetime of this nonaped, we want the first 3 pistons to extend and the 4th piston to compress. So no sinusoidal pattern here. They're just trying to pull and push according to this matrix. So far, so good. Now, obviously, I haven't told you which of these 12 pistons is piston 1. But given this idea of this matrix, do you think you could sit down and write a matrix and fill this with +1s and -1s that would get the nonaped to move forward? It's difficult, but not impossible. Anybody have any ideas? What might be a general strategy? What happens if this matrix is all +1s? What does the nonaped do? If you have an idea, go ahead and type it into chat. Even that's a little non-intuitive, hard to tell. Shall I play a little bit more of the video? As Sage says, it sprawls out, and you can see it doing exactly that in this segment. So there's a few attempts to try and get it to move. It's coordinated, it's taking steps, but not displacing. It's not moving away from the origin. Any ideas? If you could fill in this matrix in code and send it to the motors of the nonaped inside its wooden cage here, what would you send? Not so easy, right? Okay, what you're watching in this segment is the best we could come up with. So this was a project I worked on while I was at Cornell. We built this wooden cage for the nonaped, we put it in there, and we tried to create some of these matrices where you can see that we're sending different commands to the motors from 1 second, second 1, second 2, second 3, and so on. And we came up with a matrix that actually gets it to walk. But that's about as fast as we could get the nonaped to move. And given what we had seen when we send random matrices, we had a sense that there were, in the space of all possible matrices, there were some that were going to get this nonaped to move much faster. So we created an evolutionary algorithm that creates a population of random matrices. So it randomly sprinkles +1s and -1s in one matrix, goes to the second matrix, sprinkles a random collection of +1s and -1s. We have a population of these random matrices. We drop the first matrix inside the nonaped and we record how far the nonaped moves, reach into the cage, drag the nonaped back to the left-hand side of the cage, download the second matrix onto it, record how far the nonaped moves again, and we now have a number associated with each random matrix in this population of matrices. The matrices that had higher numbers, we kept those. The matrices that had smaller numbers, corresponding to cases where the nonaped didn't move so far, we deleted those random matrices. And then we filled those empty slots in the population with randomly modified copies of the random matrices that survived. What do I mean by randomly copied? Well, we duplicated the matrix, we picked a random element or a couple of elements in the matrix and flipped +1 to -1 or -1 to +1. Matt asks, are the pistons always extended or retracted like a binary state, or can they be semi-extended? They can be semi-extended, but in this case we were trying to keep this experiment as simple as possible. So the only thing the motors could do was extend the piston fully or retract the piston fully. You could send a floating point value, which is the desired length of the piston. In PyBullet, when you get to building your robot, we're not going to be using pistons. We're going to be using rotational joints like your elbow or your knee joint, and you're going to be sending desired angles. So 90 degrees, 120, 30, 0, and so on. You can do the same thing with the nonaped, but in this case we decided not to. Okay, so back to the evolutionary algorithm. We've deleted the poorly performing random matrices. We've made randomly modified copies of these random matrices, tested these new matrices on the nonaped, and repeated this evolutionary algorithm over and over. And eventually this is what we got. Oh, sorry, we're going to see the hand-designed walkers here. And then you're going to see some of the evolved solutions. You'll see that a couple of these evolved solutions are improvements on our solutions. It was basically tinkering with the timing. There's a case where the robot moves sideways. This was not something we had envisioned to begin with, but obviously makes perfect sense. So it's another reason why using an evolutionary algorithm can be useful in robotics, is the evolutionary algorithm often finds solutions, finds robot behaviors that are perfectly fine and that a human engineer may not have thought of. Okay, another reason why using an evolutionary algorithm or evolving robots compared to just fixing the body of the robot and allowing the robot to learn Thomas says, do the top 3 tubes get used in the experiment? I think not in the video you just saw. You can go and Google, nonaped, and there's plenty of videos on YouTube of the nonaped. In some of the cases, it does evolve to use to roll over and to walk using those other 3 tubes or the dorsal legs. Okay. Some of you, there's another course here at UVM called Reinforcement Learning, Machine Learning. All of these courses are about optimization methods that tune neural networks. A lot of those are used in robotics, where we have a human engineer build the robot body, like the nonaped, and then fix the body of the robot, and then allow a learning algorithm to tune the artificial neural network that controls the robot. Biological evolution obviously does not work that way. Biological evolution did not invent the human body plan and then spend tens of thousands of years tuning the brains of humans. Sapiens species, Homo sapiens species, and the other hominids and every other species on Earth, over evolutionary time, there were subtle evolutionary changes made to our body plans and our nervous systems simultaneously. Here's an old experiment. This is one of mine, where I created an evolutionary algorithm that is evolving the body of the robot along with the artificial neural network that controls it. You'll notice this robot is made of spheres. You see black and white spheres. They tell me something about the neural network control material that's inside the robot. Again, I'm showing you a snapshot during an evolutionary process. You'll see in a moment this solution that evolution comes up with, which is very non-intuitive. It doesn't seem to look like anything you'd see in nature, but it actually does locomote forward. Here's a solution where the robot is bilaterally symmetric, meaning the left side of the body looks like the right side of the body, which is a good thing usually for a body to have. But that bilaterally symmetric body plan didn't go anywhere, so it got deleted from the population, and evolution focused on this kind of odd solution. Okay. Towards the end of the course, we're going to see more and more evolutionary algorithms that modify the body and the brain of the robot simultaneously. Okay, so just to, again, put evolutionary robotics in the bigger landscape of AI, for the last few decades, the major focus in artificial intelligence and machine learning has been to take a neural network, where a neural network is made up of nodes that are meant to correspond to neurons, and edges between those nodes, which are meant to represent synapses or connections between neurons. There's been a lot of work on creating machine learning algorithms. The most powerful and the one most well-known these days is deep learning, or backpropagation of error, convolutional neural networks, all these sorts of things. What they do is they automatically tune the strength of the connections between neurons, which changes how much one neuron influences another one. But in all these machine learning methods, it's assumed that the machine learning method is tuning the connections between the nodes, but the structure of the neural network is fixed by the researcher beforehand. In the last few years, there's been an increasing focus on what's become known as the architecture search problem, which is, we're going to now, architecture search, which is now we're going to expand our machine learning algorithm to not just tune the strength of connections between nodes, but allow it to add and remove nodes and add and remove synapses as well, and search for the best architecture in which tuning the connections between nodes in that architecture causes the neural network to do something that's useful. So one way of thinking about the history of artificial intelligence is that it broadens the machine learning algorithm to modify more and more of the structure of the thing that is being optimized. Evolutionary robotics, as I just mentioned, takes that idea a step further and says, what is the body that should house the neural network to get this combined machine to do something useful. So for example, depending on what we want the robot to do, should it have wheels or should it have legs? Can we create an optimization method that can simultaneously search for the right body at the same time that it's searching for the right kind of brain, and at the same time tuning the connections within that brain? So one of the things I like about evolutionary algorithms, again, is it's sort of the broadest of all machine learning algorithms. Okay. Third reason why we might want to evolve robots rather than allow them just to learn is that we have an existence proof of a mechanism that is able to produce fantastically complex and adaptive machines. And she is Mother Nature. So biological evolution was able to autonomously, through Darwinian selection, produce autonomous agents that operate on their own. As far as we know, there's no one remote controlling us, with no supervision. So if biological evolution can produce intelligent machines, us, why can't artificial evolution produce intelligent machines, robots? Okay. Another disadvantage of learning algorithms compared to evolutionary algorithms is they often require detailed supervision. So what do I mean by detailed supervision? If a robot fails, so for example, here's an example of a biped, you'll notice it does okay, takes a few steps, but it eventually falls over. Imagine that this biped is being controlled not by an artificial neural network, but again, a simpler binary matrix where at every point in time, the motor associated with the joint is either flexing that joint +1 or extending that joint -1. If it falls over, where in the brain of this robot or where in the matrix of this robot does the problem lie? How would we know that the problem was actually here? At 5 seconds into this video, the wrong command was sent to motor 4. The left knee of the robot extended when it should have flexed. A lot of machine learning algorithms require that detailed information about being able to isolate where the problem happens, and that can be very difficult in robotics. We'll come back to that idea later. Okay, so at least four different reasons why we might want to use an evolutionary algorithm to produce intelligent or adaptive robots compared to a machine learning algorithm that only alters the artificial neural network of a fixed robot. Okay, we'll end lecture 1 with a little bit more eye candy. This is a great video reel from a few years back, which again is an evolutionary algorithm. And you'll notice here the evolutionary algorithm is tinkering with the body of the virtual agent or the virtual robot, which is determining the motor placement, where the pistons are in the robot. And at the same time, evolution is determining how to extend or compress these pistons. One of the nice things about evolving bodies and brains is it often leads to a solution that is adaptive or robust to changes in the body itself. Okay. Covariance matrix adaptation is a type of evolutionary algorithm. This is a great visualization of the evolutionary process itself. So you're seeing the best solution in the evolving population. And these champions from different moments in evolutionary time are brought together and put in the same race at the same time, which really drives home or helps you visualize evolutionary progress here. Okay. It's a great video. You can go and watch the rest of it at your leisure. Any questions about lecture 1 before we move on to lecture 2, our very short history on AI? Okay. Okay, as promised, we could spend a whole course or two courses on the history of artificial intelligence. So there's going to be a very quick crash course in the history of AI, and we are going to start several centuries in the past with a particular thinker who said "cogito ergo sum." Actually, he did not say "cogito ergo sum." He said "je pense donc je suis." He was one of the very first thinkers in Western Europe who wrote in his native language, French, rather than Latin. Anybody know who this was? Obviously, you have the slide deck, you can cheat, but for those that aren't, who said "cogito ergo sum"? Right. René Descartes posed this famous question or statement to himself, which is translated in English as "I think, therefore I am." This was sort of the end of a very intricate chain of reasoning. Some of you may study this if you take a philosophy course, where he started with this question really of do I exist, or how do I know what's really true? Very, very difficult question to answer. Obviously, we can see a lot of things out there in the environment. We see other things that look very much like us, fellow humans, friends, family, foes, and so on. But we're seeing them at a distance. We're not actually seeing them directly. There are photons that are falling on our eyes. Obviously, Descartes did not know this at the time, but he knew that the things that were out there were being reported to him, the I in this sentence, the pronoun I. They were being translated to him by a middleman, a middle person, which was his sense organs. Could you trust your sense organs? He knew at the time that obviously with drugs and alcohol and other perturbations, your sense organs can report the wrong things to you. So how can you actually trust them? If you can't trust what you see or sense or feel or hear, what can you trust? For Descartes, what you can really trust is this thing called the I, the thing that is asking the question. So the answer to the question might be ambiguous, but the thing that is asking the question, the I, must exist. There is something that is asking the question, and Descartes admitted it wasn't quite clear what this I was. However, whatever this thing is, there is something that is asking the question, and that we will call this thing I. For Descartes, this was the soul created by the Judeo-Christian god Yahweh. For others, it's the mind or the spirit. There's something in here that is asking the question, or that is receiving information from the outside world through our sense organs. That thing is real. Everything else we're not so sure about. If that's true, that creates a huge cut through the universe between I and everything else. I can trust one thing, and everything else I'm not so sure about. So for Descartes, this led to a cleavage between the soul, or the mind, or the spirit, or whatever you'd like to call it, and the body and the world and everything else. This became known much later in Western thought as Cartesian dualism. It cuts the world into two pieces, the mind and the body. It is often called the mind-body problem for a very good reason. It actually causes a lot of different problems. And we're going to see that this Cartesian dualism, it suffuses much of Western thought, and it has huge influences on robotics and AI, as we'll see. It has an influence that you can already appreciate, which is the very fact that our study of intelligence is broken into two pieces. AI, which these days are usually deep neural networks running on cloud centers, and robots, things with bodies that act in the world. AI researchers and robotics researchers are usually quite different, and they usually don't work together. So the very field of AI and robotics is already cut in half, and it's cut in half perfectly along the lines that Descartes created centuries ago. in my opinion, that is a problem. You cannot understand the nature of intelligence unless you study how body and brain work together to produce intelligent action. And we're going to study this idea of how body and brain produce intelligent action in lecture 3 when we talk about the concept of embodied cognition. Okay. This is Cartesian dualism has also been referred to by the philosopher Daniel Dennett as Cartesian gravity, mentioned by Daniel Dennett, because it's acting on it. It's this invisible force that seems to be acting on our thinking, and it warps the kinds of questions we ask about intelligence in general, and that's probably not a good thing. So we are going to spend the next 14 weeks in this class fighting against Cartesian gravity, trying to create machines that have both a brain and body, and hopefully the distinction between these two things becomes blurred, and we're going to blur that line to try and produce intelligent machines. We're going to fight against Cartesian dualism. Okay. When did Descartes say this? When did Descartes claim "Je pense donc je suis"? Any philosophy students out there? Just as a reminder, you'll see these red boxes throughout the lecture slides, and some of them are empty. This is just a prompt for you to fill in and annotate these red boxes as we go. You can either make a copy of the Google slide deck and then fill it in as you like, or print it out, or you can annotate the slides after the fact by watching the YouTube version of this lecture. No? No philosophy students? So this takes us all the way back to the 17th century. People mark the beginning of AI research at different points, but this is a pretty good, thank you, Toby. Yeah, this is a pretty good time as any. Okay, so we're going to start our discussion way back in the 17th century. Now we're going to jump 300 years forward to 1936. To Alan Turing and his formulation of what came to be known as the Turing Machine. In 1936, this was just a thought experiment. It didn't exist. It was an idea. Turing said, imagine this hypothetical machine that does X, Y, and Z. And a few years later, during the Second World War, Turing and some of his colleagues actually turned this hypothetical idea into a physical machine, which became the very first computer. Okay, for the computer science students out there, what's a very brief definition of a Turing machine? There's, I forget now, 3 or 4 different basic things that every Turing machine, whether it's hypothetical or physical, does. What are some of the things that a Turing machine does? Decidability, yes, absolutely. So this is a big part of a Turing machine. It has to make decisions. It has to decide on things. How does it decide on things? What information does it have? As Matt says, some of the information on which it decides or makes decisions is by reading symbols off the input tape, which you can see in the little cartoon image here. So a Turing machine reads symbols off an input tape. What does it do after it's read in the symbols? Moves left or right. Yes, exactly. So one of the interesting things about a Turing machine, which became physical computers, is this notion of movement right from the beginning. You can almost think of this little Turing machine here as having a body that moves left and right, which is kind of interesting. Comes back to this idea of Cartesian dualism. Inside the Turing machine, as George says, it changes its internal state based on what it read in, and also it has some internal memory. So it can combine its internal state with the symbol that it reads on the tape, combine that information to an output, and that output may cause the Turing machine to move left and right, or it may cause it to erase the symbol in front of it and write a new symbol there. Okay. However you think about it, you can sort of boil this down to the machine takes some input, does some internal processing, and then does some output. In robotics, this has become known over the decades as sense, think, and act. And we're going to tackle sensing, thinking, and acting in your robots in assignment 3, 4, and 5. Okay. Okay, so that's 1936. That was clearly the beginning of computers to begin in general, but also it laid the groundwork for robotics many years later. So jumping 20 years forward again, now to 1956. So just down the road from Vermont here in New Hampshire at Dartmouth College, a series of professors wrote a proposal to the government. They asked for a few $1,000s to hold this summer workshop in the summer of 1956. In that proposal, they proposed to hold this two-month summer workshop of 10 men, obviously this is 1950s, to study this idea of artificial intelligence. This was the very first mention of the term artificial intelligence. They proposed to hold it at Dartmouth, and this study that they were going to conduct over the summer was to proceed on the idea that every aspect of learning or any other feature of intelligence can be precisely described. And this is going to be extremely important to us moving forward. These faculty members at the time believed that you could precisely describe every aspect of learning and every other feature of intelligence. Obviously, as we know as computer scientists, if you can describe something in enough detail, you should be able to turn it into code, or in 1950s speak, create a machine that could be made to simulate those aspects of learning. You can ask the philosophical question that if you can create a machine that simulates thinking or speaking or talking or reasoning, is it actually simulating that process, or is it actually reproducing it? Is the computer code simulating intelligence, or is that computer code intelligence itself? We'll come back to that idea in a moment. But this is an important distinction to hold in mind. Are we trying to create machines that act intelligently or seem intelligent or simulate being intelligent, or are they actually intelligent? Okay. All right, so during this period, they were going to make an attempt to find out how to make machines use language. So NLP, or natural language processing, they were going to tackle. They were going to try and create machines that could form abstractions and concepts and solve kinds of problems now reserved for humans. And most importantly, these machines would be able to improve themselves. Learning or self-improvement or self-adaptation, this is obviously one of the most important hallmarks of intelligence. You'll notice that they didn't say we're going to make intelligent machines. We're going to precisely define the various building blocks of intelligence. This also laid the groundwork for future AI work, in which today you have AI researchers that work on natural language processing. You have AI researchers that work on abstract reasoning, or AI that solves the protein folding problem. You have all these specialized AI programs that simulate one or maybe two aspects of intelligence. But no machine yet has demonstrated what has become known as artificial general intelligence, right? As far as we know, we, and maybe some other species, are able to exhibit all the aspects of intelligence: language, tool use, abstraction, reasoning, planning, and so on. Okay. They believed that a significant advance could be made over these 2 months in one or more of these problems if a carefully selected group of scientists work on it together for a summer. You can imagine who this carefully selected group of scientists was: themselves. Okay, so off they went in 1956, and at the end of 2 months, how did they do? Anybody know? Any history buffs here? They didn't make much progress. They definitely did not have computer programs that could use language or form abstractions and concepts. So after the summer of 1956, they wrote another proposal to the government saying, well, maybe we need another year, maybe 2 years, 5 years. 65 years later, more than 65 years later, however long we are now, we still, 65 years later, we've still made relatively little progress on these various aspects of intelligence, with the possible exception of the last few years. The deep learning revolution and the big data revolution have produced some machines that seem to do pretty well at using and manipulating language. There was a computer program that won the Jeopardy Tournament of Champions a few years back. Maybe we're just now starting to make some progress in the last few years. So another interesting insight from the Summer Research Conference in 1956 is that researchers at that time severely underestimated how difficult it would be to make intelligent machines. You can ask yourself, how close are we to creating a chatbot that you could have an interesting conversation with? And if you weren't paying attention, you might not know whether you were talking to a chatbot or a real person. These days, you can usually tell which is which. How long will it be until a chatbot could fool a human into thinking that the chatbot is another human being? 1 year, 5 years, 10 years, 20 years? Given our history over the last 65 years, it would suggest we're not very close, but who knows? This raises this idea of what's known as thinking about thinking. And for those that took my HCI class, you've heard me mention this before. Thinking about thinking is misleading. When we introspect, or you think about your own thinking processes, it seems effortless, right? Where you can easily recognize a friend when you see them. You can easily sit down and write a few sentences. You could easily chat with a friend and have an interesting conversation over the web. Seems easy, seems trivial. Why is it so hard to get a machine to do these things? We still do not have a good answer to that, but for whatever reason, it is extremely difficult. Okay, so here are the actual attendees at this conference back in 1956. Anybody recognize any names here? Obviously, unfortunately, at that time, these were all privileged white males. Hopefully, it would be different if a similar conference were held today. So John Mccarthy. John Mccarthy actually invented the term artificial intelligence, and he created the computer program Lisp as a way to study intelligence. He believed that Lisp was a better language in which to create intelligent machines than others. Hannah mentions Claude Shannon, who became known later as the father of information theory. So information, communicating information from a sender to a receiver. Communication is clearly an important building block of intelligence. It is a form of language, or it is the mathematical description of language. So Claude Shannon was there, was greatly influenced by this group, and in turn influenced this group in thinking about intelligence and the relationship between information and intelligence. Marvin Minsky went on to co-found the MIT Artificial Intelligence Lab, which still runs today. There's been many directors since Professor Minsky. For many people, the MIT AI Lab is considered the mecca of AI. There's some fascinating work that goes on. In the after times, when we're allowed to all move around again, if you ever make it to Cambridge in Massachusetts, just outside of Boston, go and visit the Stata Center, which is the Frank Gehry building built to house the MIT AI Lab. The building itself is wonderful. You can walk through it. A lot of amazing things that happen there. Unfortunately, Professor Minsky was involved in a number of scandals around, I'm forgetting his name. Unfortunately, his name has been tarnished since then. regardless, he is a very influential thinker and actor in the early days of artificial intelligence. Some of you may recognize the name Herbert Simon, who is actually an economist and won the Nobel Prize in economics, and focused on how rational actors, like humans, make decisions. Shauna mentioned decidability a few minutes ago. So decision making obviously is another building block of intelligence and is very important. Some of you may have taken a class here at UVM with Professor Skalka. Professor Skalka was the very last PhD student advised by Professor Simon. So we've got a proud link in our family history here at UVM back to some of the founding fathers of artificial intelligence. Okay, so let's just pause from our history for a moment to think about sort of where the field has been and where it's going. If you ask different AI researchers and roboticists about what their goals are, you'll get very different answers. In the book I helped co-author, we outlined 3 basic goals. One of them is to understand biological intelligence. By building robots may become useful scientific tools for better understanding how animals and humans exhibit or acquire intelligent behavior. As we study biological intelligence, can we distill down biological intelligence into, in the case of the early AI researchers, a precise description of what intelligence is, and then turn it into code? Or similarly, abstract away all the biological details of how what Mother Nature needed to do to produce intelligence, and get down to an abstract, what is the abstract, simplest definition of the general principles of intelligent behavior. And if we can precisely describe and abstract away, we should be able to get to the point where we can apply or build those principles into intelligent artifacts. Here's a very, let's see if I can get at the volume here. Here's a very simple, very simple robot that's built from Lego Mindstorms. I think you can still buy this kit. This is going to be tricky to do here. You can program this. You can program these very simple Lego robots to either move towards light, which is known as phototaxis, or move away from light, which is known as photophobia. These are some very common behaviors you see in very simple animals. I'm sure you're very familiar with student housing, where often you have little creepy crawlies like cockroaches that when you turn on the lights in the kitchen, they run away from the light. They're photophobic. So even those simple behaviors, they're adaptive. Regardless of where the light source is, the cockroach or the robot can be programmed to always move away from the light, or by changing the wires on the robot that you see in the video now, you can change it from being photophobic to photophilic, loving light and always going towards the light. Okay, so 3 sort of basic goals in AI. Let's come back to our history and move forward from the 1950s to the 1960s and pause for a moment at Eliza. Eliza was, as you can see in the screenshot here, arguably the world's first chatbot created by Joseph Weizenbaum, and led to all future internet chatbots. I'm sure you can probably find a version of Eliza online somewhere and actually chat with her. She is surprisingly good at English conversation, or at least acting as a virtual psychotherapist. If you type in, I'm having a problem with a given family member, Eliza will come back with, why do you have a problem, or why do you think you have a problem with a given family member? So Eliza was a computer program that's built up of a huge number of if-then-else statements, where the if blocks were looking for certain combinations of verbs and proper nouns. And if that pattern was detected in the language coming in from the human interlocutor, the human that was talking, Eliza would rearrange the verbs and proper nouns, and maybe add an adverb here and there and put a question mark at the end and output that sentence. And this was a shocking finding in the 1960s, that with this non-intelligent program, it's nothing more than a set of if-then-else statements, there were certain users that would sit for hours and pour their hearts out to Eliza, and if asked about it after, would admit that they had a very emotionally, intellectually fulfilling conversation with this human Eliza that must have been on the other side of this computer terminal. A lot of people didn't realize that they were talking to a machine. They believed they were talking to a human who was typing into this terminal from somewhere else. It was pretty surprising at the time. Okay. So this confusion on the part of some of the people that spoke with Eliza has to do with another intellectual contribution that came from Alan Turing, which was not the Turing Machine, but the Turing Test. Back in the 1930s, 40s, and 50s, there were arguments going on about whether you could ever make an intelligent machine. Computers hadn't even been invented at this point. Turing made the very prescient observation that if you want to argue about whether a machine is intelligent or not, you better be pretty clear about what you mean by intelligence. And the more he pressed on that point, the more it became clear that people did not have a good definition of what intelligence is. If I were to ask you to type into chat here your definition of intelligence, often, and I do that too, the sentence is filled with adjectives for intelligence. Things that are adaptive, that think ahead, that are smart, that are capable, they can plan, they can think, and so on. But if you're trying to create a definition for something like intelligence, and the only thing you can do is use a whole bunch of other synonyms, and if you look at the definitions for those synonyms, like the definition for thinking often includes the word intelligent or intelligence. You get these sort of circular references. That's usually a signal that humans aren't very good. They don't really know how to actually define a concept. So Turing said, instead of trying to define intelligence, because we can't seem to do that, let's operationalize it. Let's construct a system in which if something can exhibit the hallmarks of intelligence, we will define it as being intelligent. And that mechanism or that process became known later as the Turing Test. If a computer can talk to another human, and that human cannot distinguish whether that computer is a computer or a human, that computer will have passed the intelligence test. It is intelligent, according to Turing's notion here, without us having a good definition of what intelligence is. The Turing test has become very famous. There's a great example of it in this particular movie. What movie are we watching? If you know, go ahead and type it into chat. This we definitely need the sound for.
Sit down.
Care if I talk? I'm kind of nervous when I take tests.
Oh, just please don't move.
I'm sorry. I already had an IQ test this year. I don't think I've ever had one of
Reaction
these.
time is a factor in this, so please pay attention. Now answer as quickly as you can.
Sure.
1187 Wintervorster.
That's the hotel.
What?
Where I live.
Nice place?
Yeah, sure, I guess. That part of the test?
Okay, for those of you that haven't seen the movie or watched the scene, you can watch the rest of this Turing test, and you can see how the test turns out in the end. Okay, we have about 5 minutes left, so I think we'll end today with the Chinese room argument from John Searle. John Searle was a computer scientist and a philosopher who had a problem with the Turing Test. He felt that it was too forgiving, meaning that he could imagine certain non-thinking entities that were clearly non-thinking but would pass the Turing Test. Therefore, the Turing Test is not a good arbiter or measurement of intelligence. And Searle made this argument by proposing a thought experiment, the Chinese room, where the Chinese room, as we'll see in a moment, is not a thinking, according to Searle, does not think, yet it passes the Turing Test. Okay, so how does this work? So we have, let's say, an English speaker inside the Chinese room. And very importantly, this English speaker does not understand Mandarin. They cannot read or speak or write Chinese characters. Okay. Inside the room, they have a huge instruction book in front of them, and this instruction book is a huge set of if, then, else statements, not unlike Eliza. This instruction book is written in English, so the English speaker can read this book, and it says things like, if you see this particular set of squiggles on a given piece of paper, then I want you to write these other set of squiggles on another piece of paper. Okay. So obviously this book is representing some sort of computer code. Imagine outside the room we have native Chinese speakers. They write a question in Mandarin, in Chinese, and they pass that question through the slot in the door to the English speaker on the inside. From the point of view of the speaker inside, they receive that piece of paper. It's got a series of these squiggles on it from the point of view of the English speaker. They find those squiggles in the book, they look it up, and they write a different set of squiggles, and they pass that piece of paper back out the slot to be received by the native Chinese speakers, who find that the response is very cogent, well written, well thought out, free of spelling and grammatical errors. It is a perfectly reasonable and human response to the question. There is clearly inside the room something or someone that is thinking, the English speaker, but they're not using their thinking apparatus in the way you would expect. They're not thinking about the Chinese question and cogitating in Chinese and writing a response in Chinese. They're basically just being used as a machine, a mechanistic thing that translates certain squiggles into other squiggles. So if we think about not the brain inside the head of the English speaker, but we think about the Chinese room as a whole, Searle challenged anyone to think that this room is intelligent. It clearly isn't. But from the point of view of the people outside, the room has passed the Turing test. Therefore, John Searle concluded, there is something fundamentally flawed in using the Turing test to try and determine whether something or someone is intelligent. Do you agree with John Searle? You can just start with yes or no. Go ahead and type it into chat. Perhaps some of you are digesting this idea. Okay, some people agree with John Searle. That doesn't seem like the room is intelligent in any way, right? We could replace this English speaker inside with an industrial robot arm that scans the squiggles and writes something else. Okay, we have a lot of John Searle fans here. Okay, we have 2 minutes left. Let me ask you a couple questions. This room is clearly not thinking. What is the definition of thinking? If this room is not thinking, this room as a whole is just some mechanistic process that's translating incoming sensory signals, which are these squiggles, and it's translating them into outgoing squiggles, which is being written by the machine or the thing. If you say it's not thinking, then your belief is that what goes on in the human head is different from the Chinese room. The Chinese room, as you can maybe imagine at this point, is meant to be a metaphor for a human brain or a computer program. If you agree with Searle that the Chinese room is not thinking, the onus is on you to demonstrate how what goes on in the human brain is different from what goes on in the Chinese room. Your brain, therefore, is not just translating incoming squiggles to outgoing squiggles, it's doing something else. Searle, when pressed, could never answer what that something else was. And in my personal opinion, again, this is a philosophical discussion. You're free to believe whichever side of this argument you want. I have yet to hear in my years of studying AI and robotics a convincing argument about what else or what in addition the brain is doing that the Chinese room does not do. I'll leave that for you to think about. You have the second quiz. I'll put that up on Blackboard shortly. It's due before midnight tonight. You are working on assignment 1. Keep an eye on Blackboard and the wiki instructions. If you're struggling with installation, I will try and update the instructions there. I have my office hours at 11 a.m. if you want to come and chat with me about that. Otherwise, good luck with completing assignment 1. It is due at 11:59 p.m. on Monday. I'll see you back here Tuesday morning to continue our discussion about the history of AI and to introduce assignment 2. Have a good rest of your day and have a good rest of your week. Okay, bye-bye everyone. Lucas, I'll save your question. We'll come back to it on Tuesday.